Welcome to G Fun Facts Online. Today, we're exploring a dramatic and powerful connection that's unfolding deep beneath our planet's serene, frozen landscapes. As the world warms and ice melts, the colossal weight of glaciers is being lifted from the Earth's crust. This incredible unloading isn't just causing the ground to bounce back, it's stirring the slumbering giants beneath, volcanoes. This is the story of how melting ice unleashes volcanic fury, a phenomenon that could create a powerful feedback loop with profound consequences for our planet. The basic concept is simple, yet powerful. Think of the Earth's crust like a flexible surface with a massive weight sitting on it. For thousands of years, glaciers, sometimes kilometers thick, have pressed down on the mantle below. This immense pressure acts like a cork in a champagne bottle, keeping volatile gases dissolved within the magma and making it harder for that magma to find a way to the surface. Now, as that weight is lifted, the pressure drops. This has two major effects. First, it lowers the melting point of the rock in the mantle, allowing more magma to be generated in a process called decompression melting. Second, the reduced pressure opens up fractures in the crust, giving the magma an easier path to the surface. The result can be a dramatic surge in volcanic activity. So how exactly does this work? Let's journey deep beneath the ice. The first key process is called glacial isostatic adjustment. Imagine the Earth's rigid outer layer, the lithosphere, as a raft floating on the more fluid, viscous upper mantle. When a massive ice sheet forms, its weight pushes this raft down. When the ice melts, the land, freed from its burden, begins to rebound upwards, rising slowly over thousands of years as mantle material flows back in. This isn't a minor adjustment. In places like North America, land has risen several hundred meters since the last ice age. This grand, slow-motion uplift is what sets the stage. One of the most direct consequences of this uplift is decompression melting. The Earth's mantle is incredibly hot, but it stays mostly solid because of the immense pressure from the rock above. If you reduce that pressure, the melting point drops. As the crust rebounds, the pressure on the mantle beneath it decreases. Even without any extra heat, this pressure drop can be enough for the rock to cross its melting threshold and begin to liquefy, generating significant new quantities of magma that were previously suppressed. While decompression melting creates more magma, changes in the crust explain how that magma reaches the surface. The weight of a thick ice sheet creates intense compression, effectively clamping shut any fractures or pathways that magma could use to ascend. When the ice melts, this compressive stress is released. The crust relaxes, and this unclamping of the system opens the floodgates for stored magma to escape. This isn't just a theory. Scientists have found compelling evidence etched into the geological records of the past. The first clues emerged from Iceland, a geological playground sitting on both a mid-ocean ridge and a volcanic hotspot. Scientists studying layers of volcanic rock noticed a striking pattern. A dramatic increase in volcanic activity coincided with the end of the last ice age around 12,000 years ago. Eruption rates were estimated to be 30 to 50 times higher than they are today. In 1996, a seminal paper by scientists Joel and Mackenzie provided the theoretical framework. They modeled the effects of removing an ice sheet and showed it would significantly increase melt production in the mantle, predicting a massive surge in eruptions. A few years later, a 2002 study by McLennan and colleagues provided the geochemical proof. By analyzing lavas from before, during, and after deglaciation, they found chemical signatures consistent with a higher degree of mantle melting, exactly what the decompression model predicted. For years, some wondered if this was just a unique Icelandic quirk. But recent research has blown the case wide open. Scientists studying volcanoes in the Chilean Andes established the first clear link in a continental volcanic system. They focused on the Mocho Chochuenco volcano, which was once buried under the Patagonian ice sheet. Their findings were a stunning confirmation of the theory and revealed a fascinating three-phase response. First came the evacuation phase. Immediately after the ice melted, there was a burst of large, explosive eruptions. This was the rapid emptying of huge magma reservoirs that had been building up under the suppressive weight of the ice for thousands of years. The pressure had also changed the magma's chemistry, making it richer in silica. High silica magma is thick and sticky, trapping gas. When the ice vanished, it was like popping the cork on a vigorously shaken bottle of champagne, resulting in violent explosions. Next came the relaxation phase. This was a quieter period with lower eruption rates of less differentiated magma. This suggests the old, stored magma was cleared out, and new magma from the mantle was now ascending more directly, without sitting in a chamber for long. Finally, there was the recovery phase. In the last couple of thousand years, eruption rates increased again as the volcano's plumbing system began to re-establish new storage reservoirs, returning to a more normal state. This landmark study from the Andes proved that the Iceland effect was no anomaly. It's a global phenomenon. So where else on Earth is this drama playing out? Let's take a quick tour of the global hotspots. We start back in Iceland, the world's premier natural laboratory for this process. Volcanoes like Grímsvötn, located under the massive Vatnajökull ice cap, have an intimate relationship with the ice. Eruptions often trigger colossal glacial outburst floods, called jökullaups. But it can also work in reverse. A sudden jökullaup can rapidly reduce pressure on the magma chamber below, triggering an eruption, as happened in 1934 and 2004. And of course, the 2010 eruption of Eyjafjallajökull, another ice-capped volcano, famously demonstrated how the explosive interaction of magma and meltwater can shut down global air traffic. Next, we head south to the Andes. The research at Mochochocuenco and other volcanoes like Puyehu Cordoncoya proves the mechanism is just as potent in the thick crust of continents as it is on mid-ocean ridges. This has turned our attention to other glaciated regions, including Alaska, New Zealand, and Russia. But perhaps the most alarming implications lie in Antarctica. The continent hosts one of the largest volcanic provinces on Earth, with at least 138 volcanoes identified beneath the vast West Antarctic ice sheet, many in an active rift system. This ice sheet is already losing mass at an alarming rate, raising the specter of a widespread volcanic reawakening. Evidence is locked in the ice itself. Ice cores have revealed layers of volcanic ash, direct proof of subglacial eruptions, powerful enough to breach kilometers of ice. One study found an ash layer from a powerful eruption 2,000 years ago that spread across an area larger than Wales. This brings us to one of the most concerning prospects, a positive feedback loop. It works like this. First, global warming causes ice to melt. Second, this unloading triggers a volcanic eruption. Third, the eruption dramatically accelerates more ice melting, either through direct heat from lava melting the base of the ice sheet, or by blanketing the white, reflective ice surface with dark, heat-absorbing ash. This is called the albedo effect. Fourth, this accelerated melting further unloads the crust. And fifth, this increased unloading can trigger even more eruptions, starting the cycle all over again. In Antarctica, scientists are deeply concerned that subglacial eruptions could initiate this exact cycle, leading to a runaway collapse of the ice sheet. The heat would weaken the ice from below, while meltwater would lubricate its flow to the sea, leading to further unloading and potentially more volcanism. So what does this all mean for our future as the planet continues to warm? The scientific consensus is clear. The removal of ice is a potent trigger for volcanic activity. The primary regions of concern are Antarctica, with its potential to significantly accelerate sea level rise; Iceland, where more frequent eruptions could once again disrupt global travel; and the populated areas near volcanoes in the Andes, Alaska, and elsewhere. A global surge in volcanism could also impact the climate. While a single large eruption can cause short-term cooling by reflecting sunlight, a sustained period of increased volcanism would release vast amounts of greenhouse gases, potentially creating another feedback loop that contributes to long-term warming. Fortunately, the geological response, while sometimes rapid, builds over centuries. This gives us time to improve our monitoring of these increasingly volatile regions. The awakening of Earth's icebound volcanoes is a stark reminder of how deeply interconnected our planet's systems are. The melting of ice at the poles is not an isolated event. It is pulling a geological trigger that has been set for millennia, urging us to listen to the rumbles of a planet undergoing a profound transformation.